As I mentioned previously, we're going to be looking at what's called the combined gas law here. And rather than memorizing or just learning all of these different gas laws here and their different formulas and which one's which, they all get combined into the combined gas law formula. Then what you have is, if you're given a problem where temperature is constant, then you can just ignore this value down here. And if temperature is constant, then we're looking at Boyle's law. And you'll notice we get the Boyle's law formula back out of it. Versus if volume is held constant, then we can get rid of the volume here. And well, now we have pressure and temperature. That's Gay-Lussac's law. And the same is true, of course, for Charles's law as well, that as long as we are holding some things constant, then we can use the combined gas law, and you can just ignore the term that is constant. I will say for all of these, in the amount of gas you have has to be constant. These gas laws don't work if you're changing the amount of gas in there. But rather than knowing which formula goes with which gas law, you just get away with having the combined gas law and ignoring the one term. If you're not comfortable with that, the other thing you can do is sometimes you'll be given, it has held at a constant temperature of 23 degrees Celsius. Well, then you can turn that into Kelvin and put that in for both sides of the equation here on the temperature. If you're not given that one, you can make up a number. I know that feels weird when you're given a problem, but make up a number. If you're told that the temperature is constant, fine. I'm going to have it be at a constant temperature of 273 Kelvin, and it'll be 273 on both of them, and then we don't have to worry about it. If you aren't comfortable with just dropping one of the terms, hold it constant, put it into both sides of the equation. You do, however, need to know each of the gas laws, and because of that, I have a mnemonic I use for learning them, and that is paid TV can be good. Well, in the top row, then, you have your initialisms for each different gas law. In the top row, you have each of your initialisms for the different gas properties. Pressure, temperature, and volume. And in the bottom, we have the gas laws, initialisms, for the different names, Charles, Boyle's, and Gay-Lussac's. And what you'll notice here, then, is that they line up, and everywhere where they line up, we have the term that is held constant. And so to me, this has always felt a little bit backwards. Boyle's law relates volume and pressure. But the mnemonic here tells us that temperature is held constant. And so each of these here, where they line up, is the value that is held constant instead. For Charles's law, it's pressure that's held constant. And that means that Charles's law is relating the other two. It's relating temperature and volume. For Gay-Lussac's law, the volume is held constant, and we're manipulating its relationship between the pressure and temperature. And so this is how I keep track of which gas law is which. As I mentioned previously, I think of the gas cylinder, and I just kind of imagine what's going on with the gas particles in there for what's actually going on. Is the relationship a direct relationship, whereas one goes up, the other goes up, as it is with Charles and Gay-Lussac's? Or is it an inverse relationship where when one goes up, the other goes down, as it is in Boyle's law? And so I don't have a mnemonic, a quick way to memorize which one is which, but if you just think about what you're doing to a gas and what the gas particles are doing in there, it should be pretty obvious these. And again, that's part of why I love the gas laws. So here we're just going to get into doing some practice calculations over these kinds of things. First thing is to just label the pieces here. A gas has a volume, so that is our volume initially. At 35 degrees Celsius, so we got to add 273 to that. That blue does not show up well. My apologies, 308 Kelvin. And then we have a pressure initial here. And then we're asked what is the volume final. If the new temperature is this, so that's going to be 178 Kelvin for our temperature final, and a pressure of that is a pressure final. Just doing a quick check here, the pressure went up, and if the pressure goes up, that's going to squish the gas, and the temperature went down, that is also going to squish the gas. So I'm expecting a final answer for the volume to be down. It is very possible to have a situation where the pressure maybe makes the gas smaller and the temperature makes the gas bigger, and you've got this tug of war, and it's harder to figure out which is going to have a bigger impact, and it's a little bit harder to do this check of your answer that I've been doing on each of these. But this one here, they both have an effect in the same direction, and so I expect the volume to go down on this one. I'm going to show two ways to work this one out. I did that once before in one of the prior gas laws and then said I'm going to do it with the way that I'm more comfortable with doing it and stick with that. So over here on the left-hand side, we'll do our pressure initial, volume initial over temperature initial is equal to pressure final, volume final over temperature final. And I know that I'm interested in solving for my volume final here. So on this one, I'm just going to do the rearrangement with the letters. So we cross multiply and divide, and you end up with pressure initial times volume initial times temperature final is equal to volume final times pressure final times temperature initial. And then I'm going to divide both sides by pressure final times temperature initial. And those are going to cancel out over here, and I'm left with pressure initial times volume initial times temperature final over pressure final. Temperature initial is equal to, and I'm actually going to put it over here on the left-hand side, volume final. Well, now I can plug those values in. My initial pressure is the 646 millimeters of mercury. The volume initial is 675, milliliters, and our temperature final is 178 Kelvin. You just have to be careful with which one's which. I almost looked up the wrong temperature there. The pressure final is 802 millimeters of mercury, and the temperature initial is 308 Kelvin. Millimeters of mercury and temperature in Kelvin are going to cancel out. I'm going to be left with a milliliters for my unit, which makes sense for a volume. In fact, they ask us to solve it for it in milliliters, and now it's just plug those numbers into a calculator, and you end up with a volume final of 314 milliliters. If you're comfortable with that, if you can jump straight to this formula, especially in your head, go for it. I was never comfortable doing that as a student. I'm barely comfortable doing that as a teacher. And as you saw, I sometimes struggled with putting the numbers into the proper place when I'm doing that. Versus solving it the other way, it's the same formula. Pressure initial, volume initial over temperature initial is equal to pressure final times volume final divided by temperature final. So then we just plug in the numbers. So the initial pressure is the 646 millimeters of mercury, and then we have 675 milliliters over the 308 Kelvin is equal to the pressure final, which is 802 millimeters of mercury, times by the volume final, which is what we're solving for. So I'm going to leave that as VF over the 178 Kelvin. Now I do the math. I do the cross multiply and divide, and so I end up with 646 millimeters of mercury times 675 milliliters times 178 Kelvin is equal to, I'm going to run out of space here, 308 Kelvin times 802 millimeters of mercury times volume final. To get volume final alone, I'm going to divide both sides by the 308 Kelvin times the 802 millimeters of mercury. Those are going to cancel out on this side. Divide by the same thing on this side, which is 308 Kelvin times 802 millimeters of mercury. Once again, our units cancel out, kelvins cancel, millimeters cancel, and I'm left with milliliters, which is what we want. And you'll notice if you compare the two sides here, numerically we have the same thing. It looks like I did swap my order here on this one. Not that it matters because order of operations says it doesn't matter. I will say if you're punching this into your calculator all in one go, which I've recommended before, that you use parentheses for everything in the numerator and divided by parentheses for everything in the denominator. But from there, we end up with a volume final of the same thing. Both methods work. I'm going to stick with using this one over here on future slides. Here we have just one more practice calculation. A sample of helium gas has a volume of 0.18 liters. So that's volume 1. A pressure of 0.8 atmospheres. That's pressure 1. We have a temperature. We're going to have to add 273 to that. And we're going to get 302 Kelvin, which is temperature 1. We're asked what is the temperature, so this is temperature 2 equals question mark. This is volume 2, and this is pressure 2. Same formula. P1 V1 over T1 is equal to P2 V2 over T2. You'll notice here I switched to using the ones and twos instead of the initials and finals, and just showing you different ways that you can do this. They're just different methods of noting what is your before and your after. B and A is another one, as I mentioned before. I bounce around between using all of them. Go with what you're comfortable with, but I found that most students don't like the ones and twos, even though that's how most textbooks do it. They prefer the initial, final, the before, after, because it makes more sense instead of calling this stage 1, step 1, and this stage 2, step 2. But do whichever one you're comfortable with. At this point, it's just plugging into the formula and then doing the algebra. And so 302 Kelvin is equal to temperature 2 is what I'm solving for, pressure 3.2 atmospheres, and 90 milliliters. I wouldn't have caught this normally. Certainly as a student, I probably wouldn't have caught it until I went to go do my unit cancellation at the end, but this is why I recommend you keep your units with you and not just plug in the numbers there, because notice we've got liters here and milliliters here, and those two don't agree. We have to have them in matching units. It doesn't matter which. Personally, I like to make numbers bigger rather than smaller, so I'm going to turn my 0.18 liters into milliliters. And so that's multiplied by 1,000, or shift the decimal 3 to the right, and we have 180 milliliters. And now our units do match, and so then they're going to cancel out properly when we go to do the math here. And I'm going to do a little bit of the rearranging in my head here, but we'll end up with temperature 2 is equal to 302 Kelvin times 3.2 atmospheres times 90 milliliters over 0.8 atmospheres times 180 milliliters. Once again, notice that the units do cancel out here when we do it this way. Milliliters cancels with milliliters, atmospheres cancels with atmospheres, and we're left with Kelvin. And so then temperature 2 is equal to 604 Kelvin. We're asked to solve for it in degrees Celsius, so we're going to have to minus that 273 to get it to 331 degrees Celsius. I didn't do a check of the answer at the beginning, so let's take a look at that here real quick. We have a pressure that went up, and so that should cause the temperature to go up. We then have a volume that went down, and that should also cause the temperature to go up. So I expect the temperature to be higher than it was to start with. We started at 29 and ended up at 331. That sounds like a reasonable answer. And that finishes up section 5.